This work is supported by the Marie Curie Reintegration Award entitled SmartMag Solutions and is a collaboration between the Bioelectromagnetics Laboratory at University College Cork and the Department of Pulmonology at Cork University Hospital. The aim of this project was to design and construct a two-dimensional electromagnetic navigator capable of steering a magnetic catheter suitable for endoscopic deployment. A second aim was to visualize the real-time position of the catheter's tip within a simple model and to demonstrate the integrated system in endoscopic navigation. Lung cancer is the leading cause of global cancer death, accounting for 1.4 million deaths annually. Suspected carcinoma will generally require further biopsy, and endoscopic access to the lung or bronchoscopy is the safest and most cost-effective method available. However, traditional approaches to endoscopic biopsy have limited range and are unable to access peripheral lung nodules where early-stage cancers are most likely to occur. Alternatives such as CT-guided needle biopsy and surgery carry significant rates of complication and added costs. The ultimate goal of this project was to develop an endoscopic navigation platform which can access peripheral lung nodules using electromagnetic steering and virtual reality imaging. The current system was designed to facilitate 2D guidance of a magnetically tipped catheter using two orthogonal electromagnetic coils. The two coils, each constructed of wound copper conductors, were characterized for both electromagnetic and thermal performance in advance of benchtop testing. A simple catheter consisting in a guide wire with an attachment of connected permanent magnetic spheres was constructed. In the presence of the magnetic field due to one or other of the electromagnets, the catheter tip undergoes a magnetic torque and can be deflected by up to 90 degrees so that the magnetic moment of the spheres aligns with the external magnetic field. Various magnetic tips were investigated. Characterization of the catheter performance identified the linear region of catheter tip angle deflection, where the tip could be accurately and consistently controlled by the current in one or other of the electromagnetic coils. The integrated system also included a 3D augmented reality view of a rigid lung model, which was used to demonstrate navigation. Navigation was by means of a gaming joystick, which controlled the coil currents and the associated tip deflection of the catheter within the lung model. The catheter deflection was initially demonstrated in this open benchtop phantom for maneuverability and control. In the final system, axial insertion of the catheter through the wooden maze was achieved with a motorized jockey wheel. By recording the angle of tip deflection from the joystick, the real-time position of the catheter tip within the lung model could be visualized in a 3D augmented reality view of the model. The catheter tip is indicated by the red cube, which moves through a library of pre-recorded data points based on the current joystick input. In this opaque model, the 3D position is only realized using the 3D representation, and this represents the ultimate clinical scenario where this platform could be deployed, that is, beyond the visual range of the bronchoscope's distal tip. This simple benchtop model demonstrates the potential for electromagnetic steering coupled to virtual navigation as a tool for accessing peripheral nodules in the human lung. Future work will seek to improve the steerability and control of the magnetic catheter, as well as implementing three-dimensional navigation in advance of preclinical testing.